If you would recall, we've been talking about the derivative of a function of two variables at a point in some rando direction v. We base this on just how f is changing in the x direction, just how f is changing in the y direction. The reason that we can get away with this, the reason that we get to focus on just what's happening in the I and j directions is that everything in R2 is a unique linear combination of I and j. I can describe everything with those two vectors, and moreover, this derivative business is a linear operator. So that's a lot that's actually going on in this statement. We get to cover everything in R2. That's the first aspect of it. There's nothing in R2 that can't be described as a unique linear combination of I and j. There's even information contained in the statement that everything in R2 is a unique linear combination of I and j. The linear combination means we're only combining I and j with these two operations, scalar multiplication and vector addition. This is important because scalar multiplication and vector addition are the two operations that a linear operator respects. Linear operators respect scalar multiplication and vector addition. That's why this matters. What we mean when we say a linear operator, when I say a linear operator respects scalar multiplication and vector addition, this is something that we have encountered in the past, even if you haven't been in linear algebra. Remember that back in the day when we were learning about derivatives, we learned that the derivative of a constant times a function is that constant times the derivative of the function. That's the scalar multiplication part. We learned that the derivative of a sum of functions is a sum of the derivatives of the functions. The derivative of f plus g is the derivative of f plus the derivative of g. So what we mean when we say linear operators respect scalar multiplication and vector addition, the derivative of a constant times a function is that constant times the derivative of a function. Scalar multiplication does not affect the process. And let's say the derivative of f of x plus g of x is the derivative of f of x plus the derivative of g of x. That's the differential operator, the derivative, respecting scalar multiplication and vector addition. So it's important that we refer to this as a linear combination because that tells us what operations, how operations interact. with our vector combination. So the derivative is an example of a linear operator. This is one of the things that we do in math. We try to look for the common properties of all the things that we do. It's not like we started building calculus with limits, even though when we teach people calculus, we start with limits. Mostly because that's the best thing that we have to explain how infinity works. At a certain point, we go from this discrete set to a continuous set, and people are like, oh, when does that happen? And mathematicians be like, it happens. And students be like, but when? And then we just read the notes and says, say it more forcefully. It happens. If not, use threats. To start threatening people. Or, oh, the instructions also say, or be dismissive. Like, oh, you'll see someday. Which is super dismissive, kind of insulting. But a way to say, somewhere. You know what I mean? So we like to categorize things. We built calculus kind of kind of backwards. We didn't start like we taught it to, like we teach it to students. Kind of the last thing to show up for calculus was the whole concept with the limits and continuity, and we're like precisely defining a limit so that we could precisely define continuity, so we could precisely define differentiability. That all came later. Kind of like we had all these numbers running around before we even had some concept of zero. We even had place value before we had zero. And I think it was India. You can't nail things down to particular people if they're that old. So it's like, well, I think it was India. They're like, oh, hey, we got this thing. It's called zero. What does it represent? It represents nothing. We have the empty set. No, not that kind of nothing. Just like nothing. Like, well, what are you going to do? You know that number 108? It's like, well, yeah, it's kind of a pain in the butt because there's no tens. Put a zero for the tens. And everybody's like, oh my God, that is so awesome. And they were like, oh, I know, right? We call it zero. Actually, I don't know what they call it. I only speak English because American. It's interesting. The reason they call them tangents, it makes more sense now that we have gradients. Because there's going off on a tangent, the function isn't changed. I just fell off onto a tangent and nothing changed. It's perfect. I love the way this analogy works. The other thing that we want to remember about the directional derivative that I've said twice before, the last 2 days, that I'm going to bring up again, is that we are looking at something that is going to be perpendicular to the contour. Perpendicular to the contour is maximum change. Tangent to the contour is no change. The dot product works because the dot product has a factor of cosine of theta. That's going to be how much of that, that's going to give us a multiple of our gradient. Starting with cosine of 0 equals 1 when we're going in the same direction as the gradient. Down to cosine of 90 If we're going in the same direction as the gradient, the angle between our vector v and the gradient is 0. Our multiplier is 1. The component of the unit vector in the direction of the gradient is all of it. So in the direction of the gradient, parallel to the gradient, we have the cosine of 0 is equal to 1. It's just the gradient. Maximum change in f. Perpendicular to the gradient, cosine of 90 is 0. Well, apparently I was thinking about trig and I reset myself into degrees. There we go. Much better. Perpendicular to the gradient, cosine of pi over 2 radians. We're going to be tangent to the contour, and that's where f is not changing. Oh, it was green. Tangent. Delta f equals 0 because the function is not changing. Question? How's everybody okay? We want to remind ourselves of things that we did before. Remember, right before this, we talked about optimizing functions. And to optimize a function, we look for a point where the two first derivatives are equal to 0. We're looking for a point where the gradient is equal to 0. It's like saying, don't go anywhere. We're at the highest points. There is no direction of maximum increase. We're at the top. Because if you're standing at the very peak, there's no one direction to go. There they are again. There's no one direction to go that will have the maximum increase. If you're standing at the bottom of a valley, there's no one direction to go that indicates maximum increase. Think about, imagine a corner in a graph. We can't just draw one tangent there. So that's why that would count as a critical point. Any questions? Comment? Deep thoughts? 11 and 14 is 25. There are 25 people in attendance in this class right now. Some of you might know the answer. I can't remember if I do this. I usually do this every semester. So some of you might already know the answer. But with 25 people in attendance, including the majority of the students on Zoom, with 25 people in attendance, what is the likelihood that 2 people share a birthday? Same month, same year. Not same year, sorry. Same month, same day. What's the likelihood that 2 people in any group of 25 share a birthday? I think about this a lot because one time I had a friend on Facebook. This is back when I would peruse Facebook, and he commented that a particular day went by and said, "Oh, wow, so many of my friends have a birthday on the same day." I looked at his friends list. He had like over 1,200 friends. I'm like, "Oh, dude, that has to happen probably a bunch of times." It'd be really weird if you had more than 300 friends and two didn't share a birthday. Because at a certain point, you just have to. If you have 366 friends, two of them share a birthday. At least one pair shares a birthday. So, what is the likelihood that only two people, I just want two, out of a group of only 25 people have the same birthday, month, and a day, not the same year? Because if some of you have a July 12th birthday, you're probably not as old as I am. Rather than precise calculations, let's just ballpark it, because humans have terrible instincts about probabilities, like to a hilarious degree. So I like to offer these 5 choices. I know I only put 3, but I also labeled them with the odd letters. Are there odd and even letters? This is a 1, 3, and a 5. So A, C, and E, those are odd letters. Then I like to put the non-committal ones, because no one likes to commit to things. Because you realize that if you get the question wrong, I'm going to take off 1 billion points and bust you all the way back down to it, but that's not going to happen. But I do like to give the non-committal answers anyway. I like to plus minus grade on this one. You know, it's kind of like, can it be both? So $25 people. What do we think the likelihood that 2 people in this group of 25 share a birthday? This is assuming that I did not, actually, I don't think I have access to any of your birthdays. I don't know any of your birthdays. It's not like I could look this up. But one time I did have twins in a class. I'm like, all right, so that would be cheating on my part. Let's count that as 1 birthday and reduce the number of people by 1. And then Michael, I don't care which one of you goes, but for the purposes of this exercise, one of you has to go. And then I go, ha, 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 ha. And I just started waiting. I said, one of you has to go. And I go, wait, what? No, I'm just kidding. You both have to go. Get out. Just kidding. Go ahead and vote in the chat if you're still there on Zoom. What do we think? Who's for slim to none? Slim to none. I mean, there's only 25 people, and there are 365 possible birthdays. 366 do that weird leap year thing. Ultimately, if you have a kid that's born on leap day, just move it to 28 first. Who's up for worse than even, but not? Actually, let's go into the middle. Who's for 50-50? Even money. 25 people. It's going to be close to 50-50. 55-45. Who's for almost certain? Who's putting almost certain just because maybe your instinct told you this, but Leach is asking the question, so I'm going to go with the opposite. That happens a lot. For the most part, people that pick almost certain are in that category. We got to vote for online for almost certain. Everybody else went back to bed. So it turns out that the answer is